Hi guys, welcome to the channel. Today I'm going to go through an International A-Level Maths P3 paper in full. Let's go. International A-Level is similar in many ways to the non-international A-Level. So if you've got mocks coming up or whatever you've got coming up, full A-Level exams, whatever you're revising for, this is going to be helpful. Just going to get straight into it. Go and find me on Instagram if you want, it's Polymath, and on TikTok as well. Okay, first question, functions question. You got some sort of function defined by something or other, and they do want us to rewrite it looks like, in a slightly different form, and then Mr. Biscoff, you really do need to just, well, that's what you just listen in for some mathematical insight as well. Yeah, rewrite it, find the inverse, and then differentiate in its simplest form. All right. Common denominator, I think, for the first one. Now, there's already an x plus 4 factorised in the bottom of the left-hand side. I think there will be, because that will factorise as x plus 4, x plus 3. So what we're going to do is times top and bottom by x plus 3 on the right-hand fraction. Isn't it? Looking good. Now we can add them together and you will get on the top 5x plus 5x squared plus, some would say, 15x. Do you want to pull out a common factor? What was happening on the top there? Oh, wait a second. You got the 15 and the 5 going to 20. Ah, okay. I see what they're going for here. I'm sharp, honestly, I have my moments. Then you can obviously pull out 5x on the top and you'll be left with x plus 4. Oh, would you look at that. It's going to cancel the x plus 4 on the bottom. Bada bing, bada bango, and then you got your answer for part A. Moving on, inverse. Well, a lot easier to do now than it would have been before. And hopefully you got your inverse certificate from kindergarten, which told you this sort of weird trick where you swap the x's and the y's around in a sort of pretty non-mathematical way. And then you rearrange it to make y the subject. So, well, like that. Multiply out the brackets. And then bring the y's together. Pull out y as a common factor. If you were just learning this, that's sometimes the hardest part to wrap your head around. And then I'm just going to write it here. Y equals 3x over x minus 5. Probably no would just rewrite it with inverse notation, just so I don't get in pretty deep trouble. For leaving it as y. Wouldn't want that. Anything else happening in this question? Derivative in its simplest form. Reasonable, a reasonable request, I would say. So if we differentiate it, do you want to do quotient rule? Do you know what? It's fine for quotient rule, this one. Yeah, it's really, really chill start. It's a kind of a warm-up more than anything. Well, there's me casually saying that. It's easy for me to say it's a warm-up. So, you know, maybe you're finding it hard. It's normal to find it hard. It's a blooming exam, so I don't know why I'm being all arrogant. That's quotient rule. I'll just write it down quickly. U dash v minus v dash u over v squared. Differentiate the top will be 5 times x plus 3 minus the bottom differentiated. Oh, that's 1. V dash u is 5x over v squared. That's x plus 3 squared. See if I can do a quick in my head simplification. 5x, oh, minus 5x. You're just going to get 15 on the top. Check that if you want to. Pretty sure I'm all right with what I've done there. And hence state whether it's increasing or decreasing, giving reason for your answer. Look, that thing can never be, it can't be 0 and it can't be negative. It can't be 0 because you're not allowed to divide by 0. There's no way it can be 0. I mean, you could have x is minus 3, then you'd be dividing by 0. Also, it can't be negative, the bottom's a square number. So, dy by dx, always positive. Therefore, increasing. All right, going to keep going. State the coordinates of P. All right. Well, it's a minimum point. The smallest that modulus can be, if it tries its hardest, it's got to be y equals 5, basically. And what's the story with the x coordinate then? Well, you need that little bit in the modulus to be 0. So you would need 3x minus 13 equals 0, so x equals 13 over 3. Not the nicest number I've actually seen today. But you know, we're all sort of beautiful in our own special ways. State the range of f. All right. Surely to goodness, oh yeah, so we're putting in all real numbers into it. So surely to goodness the range is just f of x is bigger than or equal to 5. Find the value of f of 4. Well, let's put, we'll use a little bit of working area here. F of 4, just put it in. Could I do it in my head? You never know. You never know. It looks like you'd have 12 minus 13 absolute value plus that. It's actually minus 1, the absolute value is 1, so you're going to get 6 out there. Because the absolute value of minus 1 is 1. And if you put that back in for a second time, because that's the vibe of this one, 3 times 6 is 18. Minus 13 plus 5. 5 plus 5 is 10. That's the story there. Onward, using algebra and showing you working. Show that there is some kind of nonsense going on there. Oh, I thought I was saying show, it's actually saying solve. Okay, that sounds better. Right, if we're solving a modulus one, you need to be sketching it. I'll tell you what, I'll do the actual solve first and then I'll go and check the picture, but we do need to go and check the picture. And I'm just going to solve it for when they equal each other. So I'm going to solve 16 minus 2x equals modulus of 3x minus 13 plus 5. I am then going to do my two separate solves here. So one of them is 16 minus 2x equals the positive version of the modulus. And another one here is going to be 16 minus 2x equals, covered by my face, the minus version of the modulus. Okay, solving this one. Do you know what? Well, no, I will have the calculator ready just in case my brain fails me. But moving that across, 29 minus 5 is 24, is 5x. So in that one's given x equals 24 over 5. This one, if you just multiply out the brackets, is giving, something a bit more crisp, isn't it? Because that's going to be 18 minus 16 is 2. So that's your two answers that you get there. Now let's go and check the graph. 3x is the steepness of that modulus one, whereas 2x is that one on the left. So that will be less steep. It's got a negative gradient. It's not as steep as the other one. The modulus when x is 0 actually cuts at 18. So that's 18 there. If you put an x as 0, you can check that. Whereas the other one actually cuts at 16. Negative gradient, sloping down the way, not as steep. I mean, whew, something like that. And yeah, the places where they intersect is 2 and 24 over 5. So the places where the line is bigger than the modulus graph is actually the bit in the middle here. That bit in the middle between where they intersect is where the line is bigger than the modulus graph. From a visual perspective, you always want to do a bit of visual action for modulus solving. So overall, let me just check what the question's action. It's just a solve when it's bigger, yeah. So we do need x has got to be between. In fact, if I just messed this up, well, not messed it up, but 2 is actually the smaller one, isn't it? Yeah, so it's got to be between 2 and not equal to. So 2x. I was just thinking 24 over 5 is a small number just because it's a fraction for some reason. Made me, tricked my brain there. Let me just rub those out. Swap them round. 2 and then 24 over 5. Okay, we've got part D to come as well. Can I move that away and then use this? Yeah, let's use that little skinny section again for part D. Transformation. We're moving this graph onto another graph that's got a times f of x plus b. We've got the vertex of the new one to find the value of a and b. All right. Transformations. Vertical stretch, that a at the front, and horizontal shift, that b inside. So if it goes to, what did it start off as again? So 13 over 3. Well, oh yeah, so we're just allowed a stretch and a shift. So let's do the x coordinate first. It's got to go from basically 13 over 3 to 4. What is 13 over 3? That's about, oh yeah, it's 4 1/3, isn't it? 13 over 3 is 4 1/3. Yeah. Sounds all right. So if it's moving from that to 4, b must be 1/3. That would shift it to the left by 1/3. So b is 1/3. And in terms of a vertical stretch, we're going from 5 to 20. So a has to equal 4. Yeah, 1/3 moved to the left and a stretch by 4. Next question. Hydration. Total mass of gold tons extracted. We're mining today. Quite a steep drop off on the old gold mining towards the end, it looks like. I've obviously cleared the whole mine. Okay, we've got a model, blah, blah, blah. Find the value of k. T is bigger than or equal to k. Okay, so that's when g equals 0. Should we just solve that, shall we? Come on then. 40 minus 30 e to the 1 minus 0.05 t. Funky equations. people are coming up with in this day and age, equals 0. So a couple lines of work and you'd get 4/3 equals e to the 1 minus 0.05t. This is your moment to shine. Take ln of both sides. And swap that round. Algebra fest. Could divide by 0.05 or what is it? Times by 20? Give you the same thing, wouldn't it? Yeah, times by 20. So basically t is 20 times 1 minus ln 4/3. Calculator at the ready. One minus ln 4/3. 14.246. Not really the nicest value of k. I guess you could keep it as an exact value like that, or whatever you need to. It's not really pleasant, is it? Unless I made a mistake. I might go and check it in a second. I might go and check it. Set it equal to 0, moved it across, so it's 4/3, ln both sides, and then solve it. Yeah, and t is years, is it? Fair enough. Hence, find the year and the month in which the gold started being extracted from the mine. Goodness gracious me. Well, let's just keep that as 14.2, okay? Let's move this away again. Da-ba-dum. So it's just a case of doing 0.2 times 12, I think, would be the best. 0.2 times 12 is 2.4. So that seems like February to me. How do you spell February? Something like that. The year and month. So that's for the 0.2 part, and the 14 years, it's 14 years after 1st of January 1800. So there you go, that's the year, and it's February. Hence find the year and month in which the gold started being extracted. First of January, let me just think about that. 0.24, should we have kept the 24 there? Times by 12, does that make a difference? 2.88. So the first, well, if you think about it actually, after that, sorry, I'm just having a mild panic attack. It's March, isn't it? Because we're into the 3rd month. That's it. It can really do you that. It can really screw you. It can really snooker you, that one, can't it? Because if you think about it, start on 1st of January. 1 month would take you to 1st of February. That's 1 month. And then 2 months would take you to 1st of March. So 2.4, you're actually in March. It's like 2 months have been completed. Well, I never. Glad I caught that one. State the value of the limit of the mass of gold that can be extracted. Oh yeah, that's a cool little question. Good one to know about the sort of limiting properties. Let me even just write out the thing again. It is G equals 40 minus 30 times e to the 1 minus 0.05t. So really what you're looking at is the property, or the value of this thing as t goes to infinity. That 40 is not going to change, so the question is what's happening to this expression. Now I could kind of take it apart and analyse it a little bit more. But basically, the 1 is going to be irrelevant. If t is 1,000,000, you got 1 minus 5,000,000. It doesn't really matter. So actually, that goes to e to the minus infinity, which is, I mean, this goes to 0 basically. You could also think about it as like 30 over e to the minus a very big number. Is when the denominator gets very big, the term goes to 0. So yeah, that whole second term is going to go to 0 and the limit's 40. That's the limit to what the gold can be extracted from the mine. Why am I singing today? I'm not really sure. Got up on the right side of bed, ready for some trigonometric solving. Show that old chestnut equals that old chestnut. All right. You know, not rushing to show off. However, addition formula, 2 sine theta cos 30 minus 2 cos theta sine 30 equals 5 cos theta. Let's put in my exact values. Cos 30 is root 3 over 2, so that will be sine theta times root 3. Let's put it at the front. Oh, that's just cos theta, because sine 30 is 1/2. 5 cos theta. Then you bring it across and you'll have 6 cos theta. And if for any sort of grand finale you want to divide both sides by cos, well yeah, if you divide by cos and divide by root 3, you'll get sine over cos is tan, so tan theta equals 6 over root 3, which is 6 root 3 over 3, which is 2 root 3. How did I do that last bit? Just with my third skills from yesteryear, times top and bottom by root 3. Keep on moving, some have said. Hence or otherwise, solve that beast. The main thing with this is, look, it just happened in my brain there immediately. Compare, this one with this one. What's happened? Particularly if you look at the cos one, that's probably the easiest to see it. And what's happened is theta equals x minus, plus 20. So really, we are solving tan of x plus 20 equals 2 root 3 between 0 and 360. At least it's only between 0 and 360, eh? So that's not too traumatizing, hopefully. Click in with your trig solving. Inverse tan then of 2/3. 2 root 3 really. That's what I should have said instead of 2/3. But anyway, can't take that back now. It's what's done is done. So you got 73.9 to 3 significant figures. And then your other answer is going to be add 180 to it for tan, or 254 to 3 significant figures. And then you add on 20. 93.9 or 274. Let's just have a look. The thing is, why would you add 20? I'm not really sure. You got to subtract 20. You've got a plus 20 on the left hand side. 53.9 or 234. Second time lucky, many would say. Anything else in that question? Not especially. Addition formula, a little bit of trig identity, but it's not the hardest one ever. Then a little bit of a substitution. I think that theta equals x plus 20 is really the crux of that. And then you can just do a normal trig solve, and hopefully you remember to do minus 20 instead of plus 20. You might, you never know. Law of statistical averages, it might eventually kind of work out. Integration. That's what I like. I like a nice crisp not too many words in the question type vibe. So do you know what? We're off. Find by algebraic integration the exact value of that. And then we're doing some other integration. All right, come on then. I'm up for it. I'm up for the challenge. Also exact value. Looks all right, that one. Look, you know, I know integration is just a little bit of a wilderness. But there's no x on the top. So you can just go back to your nice, crisp, classic integration-y trick stuff when it's kind of in a linear form without too much drama. You could do substitution if you really wanted to, but it's a bit excessive. I would just be saying add 1 to the power, minus 2, divide by the new power, which is minus 2, and then also divide by the derivative of what's in here, so it's an extra 2. So that one more time. Add 1 to the power, divide by the new power. That's just differentiation. Sorry, that's just integration anyway. And then you just got to do an extra divide of the derivative of what's inside there. You can only do that when it's linear, i.e. it's like just 2x there. If it was x squared, you wouldn't be able to do that. But anyway, I'm not going to bleat on about that too much. It's a kind of relatively quicker one. 8 over minus 4 is minus 2. Definitely ask me about it in the comments or berate me about any of this stuff if you want me to go into more detail. Or you got anything else you want to, any other insight you want to add? That's looking good. Just put in the 4 and the 2 now. Not totally sure why it's banging on about exact value, but anyway, we go with it. Minus 2 over, let's do instead, when we put the 4 in, 8 minus 3, so it's going to be 5 squared, minus 2 over 1 squared. All right, so basically minus 2 over 25 plus 2. So that's really just 50 over 25. It's 50 over 25, right? So 48 over 25. I mean, it is an exact value. Usually I would have thought exact they're wanting for like they'd want a root or something like that, but they've not come out looking for a root today. They have not come out on that mission. Find in simplest form this other integral. To me, it's 2 marks. It's a little bit of a trigger alert. I just think if you can notice it, it's integration by recognition, reverse chain rule, call it what you want. Because if we start with this, yeah, anyway, sorry, notice that the x is roughly the derivative of what's inside there. If you differentiate what's inside, it's 2x. So up to a factor of a number, it's roughly the derivative. That makes me think, add 1 to that 7 and try this. Why don't we just try differentiating that and see what happens? You would get 8 x squared plus 3 to the 7 times 2x. So you've got 16 at the front there, an extra 16 that you don't really want. So therefore your answer is 1 over 16 x squared plus 3 to the 8 for your integral. You could say test here if you want. So your answer is that. I don't really want to go into like majorly a much more detail than that right now. Again, could be something to explore in future, but for time purposes, I'm moving on. Reverse chain rule, that's called. And for 2 marks, I think that's the one you want to go for. Funky graph, I would have no idea what that looks like. A combination of quadratic and ln. Fair enough. Show that it has a stationary point there where p is a constant to be found. Okay, we're differentiating, aren't we? dy by dx equals 0 for stationary points, turning points, minimums, maximums, call them what you want, when you want. If you do differentiate that, you're going to get dy by dx equals basically 3 over x squared minus 5 times 2x. That's chain rule. That is turbo chain rule, where you differentiate the outside thing, so ln goes to 1 over, and then you multiply by derivative of the inside thing. Keep going, minus 8x, and the 15 disappears. And that's got to equal 0, as we mentioned here. Tidying it up a little bit. Basically, 6x over x squared minus 5 and minus 8x equals 0. Bring, what we're going to do, bring that 8x across, and then also times by the x squared minus 5. Multiply out. Well, should we multiply out? Nah, let's not multiply out. Let's totally abandon what I've just done there. Let's just multiply everything by x squared minus 5, because then you would get 6x minus 8x times x squared minus 5 equals 0. The reason I've done that is because now I can pull out common factor of 2x, I guess. 2x brackets 3x minus 4 times x squared minus 5. You see, just a little bit nicer in terms of factorizing. We press on. Yeah. So you've got either this equals 0, so you've got an x equals 0 situation. Is that allowed? X has got to be bigger than root 5. And then here, assuming I've done my sort of signs right, which I'm feeling reasonably confident about, we do have minus 4x squared plus 3x plus 20 equals 0. You could try and factorize that. Time is of the essence. You've got to give it a go in your calculator. Is your calculator going to give you roots? That's the only thing. If my calculator gives me decimals, I'm going to have an absolute fit here. Nah, it didn't give me it. But it did give me pretty horrible answers. Let me see what the thing is saying. Show that is a stationary point. X equals root p over 2. Nah, I've done something wrong. Surely to goodness done something wrong, so let's go and check it. Right, differentiated that. Yep, 3 was still on the top. Multiplied by the derivative of what's inside 2x. That goes to 8x equals 0. Fair enough. Now from here, times by x squared minus 5. Cannot complain. Who could possibly argue? Few people that I know. Then I pulled out that as a common factor. Ha 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 ho 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 ho. He 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 he. There's an extra x. So that'll just be 3. Okay, okay. Everyone just relax. Just chill out, will you? And then that will be 4. Yeah. Should we try it again? So now you've got minus, should be easier this time actually, minus 4x squared equals, sorry, plus 23 equals 0. So you do get then x squared is 23 over 4. So x equals root 23 over 2. That's better. It wouldn't be the minus 1 because x has got to be bigger than root 5. All right. Onward. Different curve. All right. Wow, we move on fast in this place. So it's just the end of that one apparently. Y equals 4x minus that old chestnut. Again, oh, it's just an absolute differentiation fest, isn't it really? Come on then. dy by dx, excuse me, is 4. Chain rule minus 24 sine x cos x. Done that a little bit on the quick side, but yeah, chain rule, I guess, don't want to, again, just for time, I don't want to go into too much detail. However, it's the same as 12 times sine x squared. So you're multiplying the two, take one off the power, and then multiply by derivative of what's inside. Chain rule. It's not equaling 0 this time. It's basically 12 sine 2x, because you've got your trig identity, which is sine 2x equals 2 sine x cos x. All right? Get a tattoo of that immediately. Hence, find the maximum gradient of this curve. It's not wanting the maximum point. That is sneaky stuff, isn't it? Maximum gradient. So, oh, maximum set equals 0 maybe. No, you're not going to do that. Rather, it's saying, look at that. The highest, and it's to do with the sign. The highest sign can be is 1. But there's a minus here, so that would actually have the effect of making it minus 12. That makes sense. But if we take the minimum value of sine, which is minus 1, you can quickly do 4 minus minus 12 is plus 12, so it should be 16. You could differentiate again, set equals 0, and it's not really worth it. When there is sine comes up like that, or sine or cos trig ones, and they're talking about maximum minimum value, just kind of trig modeling-y things, you do want to be able to use that fact that the maximum of sine is 1 and the minimum is minus 1, but then use it in the context of the question, which could involve minus signs as well. Oh, goodness. These glasses are dirty. There's no two ways about it. There's no two ways about it. Onward. Log modeling action. What we're doing, species of trees. I'm not all that into botany yet, but I'm always looking for new hobbies. Find the mass of this tree given your answer, 2 significant figures. All right, so we're just subbing in 45. Is it in centimeters already? It is in centimeters already. I'm so happy. I'm so happy. Log to the base 10m equals. I think we just plug it in, to be honest. I know you could kind of play around with it maybe. I'm going to just plug it in to begin with and see if I'm happy with the numbers that come out. 1.93 times log to the base 10 of r. R is 45. Plus, after you've done that, 0.8684. So you get on the right hand side 3.8747. I might just keep that on my calculator, because the way to undo it is going to be 10 to the power of that. So if I just do 10 to the power of answer, clever stuff really, you'll get 7494. 2 significant figures, 7,500 kilograms. Show that the equation for the model can be written in that form. That is quite loggy type stuff, isn't it? Classic loggy stuff. Which way do we want to go with it? Let's basically actually, better way, maybe start with this, right? Start with the one that they've got. If you do m equals PRQ, log to the base 10 both sides. Log rules on the right hand side. Another log rule where you bring that q down the front, q log 10r. And now the reason for doing that would be to compare it against what they've got in the question up there. Maybe I'll just write it in different colour underneath it. Whoa. Do you know what? I see now and again I actually do like good working. It can happen. Right, I'm going to suggestively write it though the other way around, because you've got 0.684 where there's no r, and the one that has got an r is 1.93 log to the base 10r. Well, that's pretty good because you can immediately see what Q is. Pretty happy with that. Q equals 1.93, but for the other one, comparing it, you do need to say that, well, you'd have to do a couple lines of working. Log to the base 10 p equals 0.684, so p equals 10 to the power 0.684. Does that give me anything remotely sort of nice? 4.83, I could work with 4.831. I could work with 4.831. 4.83, 4.831, three significant figures. Okay, 4.83. So m equals 4.83 times r to the 1.93. With reference to the model, interpret the value of the constant p. It's the initial value, isn't it? It's quite often the initial value. Why does that make sense? Let's have a look. No, it's not the initial value. If you put in R0 in this case, you would get 0. So the initial mass is actually 0 in this case. It looks like to me, unless I've made some sort of catastrophic error with my life, which I'm not sure that I have. So rather, I would say, let me just tell you the answer, then explain why. Height after 1 year. Maybe I could spell height if I tried. After 1 year. Times in years, isn't it? Oh, there's no time. Let's try again. Totally try again. That's just couldn't be wronger. Don't think wronger is a word. Let's go again. Mass when radius is 1. Centimeter. I think that's all we can really say, because if you look at it, if I put in r as 1, that will give me 4.83. That's the only time you get 4.83. 4.83 is not, so it's not the initial amount. That would be when r is 0 and it's 0. It's not like it's not a ratio or anything like that. It's not how much it grows every year. So I think all you can say is mass when radius is 1 centimeter. Okay. Oh, bit of arc signage. Bit of arc signage. Just moving it to suit my needs. How are we doing for time? I'm not really sure how long we've been going. Let's just keep up the pace if we can, all right? Sketch. What do these graphs look like? I don't always necessarily carry it around in my head, but I do remember that a sine graph looks like that. To take the inverse, you do cut between here and here and just take the inverse of that bit, and the inverse does look like that thing reflected on the line y equals x. There's the line y equals x. So all in all, get rid of all the rest of the stuff. It's got to look something like that. The half x shouldn't change the shape particularly much, a bit of stretching or whatever, but that's all right, I think. And we're going between -2 and 2. So yeah, we could put in like that, so obviously y over 2 there, and minus pi over 2. And does that work? If you put in x as 1 and -1, yeah, that's fine. So that would be 2 there, and -2. Given that something or other, show something or other. Sounds good to me. Oh, can maybe put that sketch up the top. with the, there you go. Okay, dx by dy is 2 cos y. So dy by dx is 1 over 2 cos y. We just need to change into x now. That's the only thing. We've got our derivative in terms of y. We need to change it into x. I would just use the original thing again, squaring both sides of x equals 2 sine y. X squared equals 4 sine squared y. So x squared equals 4, 1 minus cos squared y. Play around more. Continue to play around as required. And you should end up seeing that cos y equals, here's me trying, it's going to come back to bite me. Trying to, well, no, let's do extra lines of working, right? There's no point. It's a false economy trying to skip lines of working. I would probably give you guys in trouble for doing that, so let's just do it all nice and accurately. There you go. Square root of 1 minus a quarter x squared. So if we sub that in now, dy by dx equals 1 over 2 times the root of 1 minus a quarter x squared. Just playing around with this to get the numbers good. Let's put the 2 inside, which is like, well, let's just do a couple lines of working, which is like putting it as 4 inside the square root. And then if you multiply it, you would indeed get 1 over root of 4 minus x squared. So it should just be 4. What else we got? The point P lies on C. There's a y coordinate. Find the equation of the tangent to C at P. Fine. If that's the y coordinate, let's get the x coordinate. X equals 2 sine of pi over 4, root 2 over 2, so you're just going to get x as root 2. Can't hugely argue with that. Do we also need to get the derivative as well? We probably do, so we need to sub in our x into the derivative. dy by dx, if you put in root 2, it'll be 1 over 4 minus 2, so it's 1 over root 2, which is root 2 over 2. So, where am I going to do it? Here. Y minus y1, your point is pi over 4, equals m x minus x1. Straight line, there you go. Y equals root 2 over 2x. Oh, that goes to minus 1. Plus pi over 4 minus 1. Looks alright, doesn't it? Looks pretty good to me, if you ask me. End of that question? Yeah, onward. Couple more left. There's a graph, find the derivative. Oh, and then it's going to end up being iteration. Not too many marks for the derivative. We'll just try and do it alongside here. Pretty long, but product rule, why don't we rewrite it as x cubed minus 4x e to the minus a half x. Then we can do product rule. The derivative, differentiate the first thing, that will go to 3x squared minus 4. Keep the second thing the same. Plus, keep the first thing the same. Differentiate the second thing. Product rule. Alright, didn't even really tell us to simplify it, so I'm just going to leave it like that. I mean, come on now, 2 marks. If you want more work from me, then give me more marks for it, for goodness sake. Cannot believe these guys. Chancers. Absolute chancers. So, got the derivative. The line is a normal to the curve at O and meets the curve again at the point P. I think we need the equation of the normal. So the x coordinate of P is a solution to that equation. Yeah, we need the equation of the normal as far as I can see. So let's get the equation of the tangent at 0. Let's just put in x equals 0 into our derivative. And you would get 0 minus 4. You're just going to get minus 4 there because e to the power of 0 is 1. Plus, oh, is that just an absolute zero fest? I would say that's just an absolute zero fest over there. Because you got 0 and 0 minus 0 is 0 times whatever. So, bam. So derivative of the tangent is minus 4. It doesn't make any sense, does it? Doesn't make any blooming sense because, no, it does make sense because the tangent is going down that way. It's obviously going to be minus 4. Okay, fine. I was going to say it didn't make sense because this was a positive gradient, but that's the normal, and that does make perfect sense because m1 times m2 equals minus 1 when they're perpendicular. So that means the gradient of the normal, let's call that m2, is basically a quarter. And actually it goes to the origin as well, so to be quite honest with you, it's just got to be y equals a quarter x.
Good evening, Paul. Sorry, I don't have an answer.
Alexa, stop. Please don't interrupt me again when I'm doing important gradient work. Some people, honestly. So, y equals a quarter x. Where are we going to go from here? Set it equal to the original equation, isn't it? Surely. It's got to be. Quarter x equals x, yep, and so on. Got to get it x equals, how dissimilar is it to that or not? There's a blooming square root involved. Because it's almost x equals as it is already. But the only thing that's, it's not the form that they're wanting it in. I'm going to have to get that x squared equals and take a square root. Anyway, let's basically just go for it. I'm in a couple of minds here. I'll divide everything by x. Don't really like to divide everything by x. Are we allowed x as 0? You kind of should be able to have x as 0. That's clearly as somewhere where they do meet. So I guess you could maybe do it by factorizing. Yeah, it's a little bit, I feel a bit naughty, I feel a bit sort of dirty dividing by x here. I feel like I'm losing a solution, but I guess you could say, well, I know that x equals 0 is a solution. So, and it's not the one that we're looking for. We're actually looking for p. So I'm just going to do that. But I'm going to feel pretty dirty while I'm doing it. Do that times now by e to the positive a half x, which will cancel that out and you'll get it on the other side. A quarter e to the half x equals x squared minus 4. So x squared equals a quarter e to the half x plus 4, and then you can take the square root. Now how similar is that to what they've got? Yeah, they've got a half on the outside, 16 on the inside. Okay, we'll worry about that in a second. Square root of, let me put the 4 here then, plus a quarter e to the 1/2 x. Okay, so we're supposed to get a minus on the outside as well. We did take a square root, admittedly. Why is it coming up with a minus answer? Let me have a look. No immediately clear reason. The point P is in quadrant 3. Yeah, why would it have to be the minus answer? Let me just check it again. You've got that, divided it through, multiplied, cool, so that's gone. Got your x squared plus 4. I guess you could say when you're taking that square root that there's, yeah, you could say there's 2 possible answers, like it's plus and minus. But no, I don't really know about that. Keep going, we'll worry about that in a second. Let me just see if I can get the number right first. So you could write it as square root of a quarter times, oh, then that would have to be 16 plus e to the half x, like that. And then you can take square root of a quarter, which is a half. So that's all very well and good. But let me see if I can work out what's going on. How do we know to put the minus in when you take the square root? Is it just visually from the graph? There could be plus and minus answers, I guess, like I just said. Maybe when you do the plus one it doesn't work, and when you do the minus one it doesn't work. I can't see any immediate reason from the algebra why in your right mind you would choose the negative square root, except from just looking at the graph. So I'm just going to write the negative when I take the square root, just because it's kind of wanting me to do it. Could be an element of trial and error as to why they came up with that. Okay, but fine. Now we've got the iterative formula. Find the 4 decimal places, x2, and the coordinates of p. Okay, can work with that. Ci x1 equals minus 2, x2 equals, plugging it in, minus 2 equals, then you have minus a half times square root of 16 plus e to the power of a half times answer. Oh, I think I did it wrong. Let's try again. Minus 2 equals, then minus, minus a half. Talk amongst yourselves. It's kind of part of the skill, calculator skills, just making sure you put it in all okay. If I press equals once, I am getting minus 2 point, how many decimal places? 4. 0, 2, 2, well, it's 8, 6, so 9. And then if I keep pressing that until it stabilizes, the actual x coordinate of p is minus 2.0226. Cool. Yeah, I'm a little bit mildly upset about the minus sign, but I just can't see any reason they want us to justify why it's a minus here. I think that's just them helping us out a little bit, that you would get a plus and a minus answer there, but as you can see from the graph, if you took the plus one, you wouldn't get any solutions for that. It doesn't cut anywhere else with a plus x coordinate, whereas it does cut with a minus x coordinate. So yeah, I don't think they really want too much from us there, but it is mildly disconcerting. Last question, come on. Oh, make it a good one. It's a double camel hump with a sort of wee hump in the middle. What on earth graph is that? Wow. Show that that is that. Trig identity. Okay, got my second wind. I'm off. 10a. Multiplying out the brackets. 1 plus 4 cos 2x plus 4 cos squared 2x. Okay. So I think we're kind of all right. It's maybe just changing this one into the cos 4x. Well, let me put the identity up. Cos 2x. Just checking if you can see me there. Cos 2x equals 2 cos squared x minus 1. So if we want 4 cos squared 2x, I can sort of manually, well, let's times everything by 2 first. You'd get 2 cos 2x equals 4 cos squared x minus 2. And then let's, instead of putting this singular x in there, let's change that to 2x. So you'll have 2 cos 4x equals 4 cos u squared 2x minus 2. So 4 cos squared 2x equals 2 cos 4x plus 2. There's a little box of working for you. I'm going to sub that in. One plus 4 cos 2x plus 2 cos 4x plus 2. So effectively, that 2 and 1 just come together in perfect harmony to become 3. 2, 3, 4. Poetic stuff. Come on then, let's finish strongly. What are we going to do something with that? Is that hence? That curve touches the positive x-axis for the second time when x equals a. They put that on the picture already. The region's bounded by the curve on the y-axis and the x-axis. Okay, so some sort of shaded piece there. Find using algebraic integration and making your method clear the exact total area of that shaded region. Fascinating stuff, I must suggest. So I think we do need to find a then. We're in a good place to integrate that. We'll be able to integrate that in a minute, but I think we do need to find a. Is it worth differentiating it? Or can we maybe just look at the cos graph and deduce what the x coordinate has to be? I'll tell you what, I'm just going to be a bit formal. It's probably not necessary, right? But just for the fun of it, I'm going to be a little bit formal and differentiate that. dy by dx equals 2 times 1 plus 2 cos 2x. If we realise this is excessive, then I will stop and abandon it, but multiplied by the derivative of what's inside minus 4 sine 2x. Yeah, I think I will abandon that, because look, if you multiply that out, it's going to get overly complicated. I was going to set that equals 0 and then try and solve it or whatever. I'm abandoning it. Too complicated. Let's just focus on the equation and think about cos 1 plus 2 cos 2x. Well, your first sort of high point there is obviously when x equals 0. Fair enough, and you'll just end up with cos of 0 is 1. So you'd actually end up with 3. It'll be 1 plus 2 if you put an x as 0. Now, when's it going to get to its next low point? You're going to have a low point. Oh, and then you're squaring that actually, sorry, so it's going to be 9. Yeah, and so next you're going to have you're going to have a place where it cuts when it's actually cut 0. So when that thing's equals 0, this would have to be minus, yeah. I think that's the important thing. I think that's the important thing, isn't it? It's when y equals 0. Maybe I should have arguably seen that quicker, but we're in now. So when y equals 0, 0 equals 1 plus 2 cos 2x squared. So square root 1 plus 2 cos 2x. Rearranging, cos 2x equals minus 1/2. You know, it's a marathon, not a sprint, okay? And sometimes it's like that. Look, I still do that sometimes. You try one method, it's not quite working out, try a different one. Try another method, no, it's not quite. Sometimes it's just about knowing when to stop and abandon your method and go back and try something else. I think I found it okay this time though, because we're solving cos 2x equals minus 1/2. And basically, if you did inverse cos of that, your first few positive answers are going to be, what's inverse cos of 1/2? 60 basically, isn't it? Now we're probably doing radians unless we're told otherwise. Yeah. No sort of thought of it being degrees. So inverse cos of minus 1/2. Second quadrant, 60. 180 minus 60 is 120. 2 pi over 3. And what's the other one going to be? It's pi plus pi over 3. 4 pi over 3. Do we need to do anything else? Probably not. Because you've got your yeah, it's the second one. It's the second time when it hits. The second positive place when it hits 0 is A. Okay, so divide by 2 now. Pi over 3 and 2 pi over 3. So this one has to be A, the second one. Okay. Now we can integrate. Come on. And we've done the hard work, excuse me, in part A. So hopefully it's not too bad to integrate between 0 and 2 pi over 3 of 3 plus 4 cos 2x plus 2 cos 4x. Let's move this along a little bit and go for it. 3x plus integral of that is 2 sine 2x plus 1/2 sine 4x between 2 pi over 3 and 0. Let me just read in case there's anything with exact values. The curve touches. Yeah. Find using algebraic integration the exact total area. So that's a kind of trigger of, we can't really put it in our calculators. We got to go manual. I'm quite keen on a bit of manual action, so let's do it. I'll slightly fast track it. 3 times 2 pi over 3 is 2 pi plus sine of 4 pi over 3. Let's just do that in the old calculatorinos, I think. Yeah, I'm now in radians. So sine of 4 pi over 3 is minus root 3 over 2. And then you're timesing it by 2, so that'll just go to root 3. And what we got here, sine of, let's just keep it in the calc, basically 8 pi over 3 is root 3 over 2, and you got another half, so that's really root 3 over 4. Minus, when you put in 0, you'll have 0 plus 0 plus 0. Well, that's nice of them, isn't it? Oh, Well, I was going to say it's almost 3 separate terms, but no. That root 3, you could rewrite it as what? 4 root 3 over 4? So 4 root 3 over 4 plus 1 minus 4 or something plus 1 will be minus 3. So 2 pi minus 3 root 3 over 4 is looking like the exact area. All right. Thanks very much, guys, for joining me for that. That was quite enjoyable. It's a lot of brain power, you know. I'm jealous of you guys out there doing these exams in one sense, but on the other hand, I do quite like just sort of lounging around and napping, so without expending this much energy. So well done. Just a quick recap of that last question before we go. First part was a trig identity. It's just multiplying it out. I think the only quirky part of it was this bit on the right hand side, where you're having to deal with cos squared 2x, and it's a bit weird. So okay, you can use your double angle formula for cos, but you've got to slightly modify it to deal with the fact that it's cos squared 2x instead of cos squared x. Anyway, we dealt with it in that box. Then for part B, the first funky part was, even for me, what is the best way of finding A? Now, I initially thought, oh, do you know what, it's a blooming turning point, so that could be a way to go about it, but when I differentiated it, it just looked complicated with the sine and the cos. I just thought it's not the way to go. And then I had an epiphany from up on high, and that was, it's hitting the x-axis, so y must be 0. So when I set y equals 0, as we can see in this box, what happened? Oh yeah, well, the squared didn't really matter anymore, and it ended up being cos of 2x equals minus a half. You learned that in kindergarten. You've got to have some sort of method for solving these trig things. I kind of just did it a little bit in my head, which is maybe not the most useful for all involved, but anyway. 2 pi over 3 and 4 pi over 3, divide it by 2, and took the biggest answer, because if you look at the picture, it's the second positive one where y equals 0. Then we just did a nice normal integral, which wasn't too crazy, but we did exact values and we left our calculator in the bin. Thanks very much, guys. Pleasure. Thank you for joining me, and I'll see you next time. Bye-bye.